All right, welcome back, everybody. Um, this is the lecture for sustainable engineering and hydro. So I have a PowerPoint I want to go through. I want to talk about estimating the potential energy output of a hydro system. I think I have three ways or three methods that I have found to do a basic estimate of a hydro system. But I want to talk about the system first and how they work, and then go from there. So I'm going to minimize myself a little bit. Obviously, a hydro system is going to involve some kind of dam or some kind of reservoir. So it can be a natural reservoir, like, Bull Run Lake, for example, is a natural reservoir that we use for water supply to Portland. Had some hydro capability at one time, but that went away. But the Columbia River, for example, is a natural flowing river that we've dammed up to make essentially a reservoir or a collection of potential energy. Remember, potential energy is just the energy of weight and that weight's ability to fall. So when weight falls, it uses energy when it falls. So we can try to capture that and then turn it into electricity. Almost all of the sustainables that we're going to talk about from here on out, other than solar, is going to involve spinning a turbine. And a turbine is a mechanical device that turns a rotation into electricity via electromagnetics. So I'll actually make one of these. I'll make a video of making one of these. We do it in class. When this class is offered in person, you actually make a energy device out of rotating energy. So all of these sustainables, wind, geothermal, hydro, wave, they all turn rotational energy into electricity. So if you can spin something, you can create electricity. So let's look at this dam, and how it works is we collect water, right? We hold it back, create a depth, and then we drop that water down these columns of, down these tubes or columns into a turbine, and then the turbine spins. So when we have a spinning turbine, we create electricity. So that is all hydro does. It can be in giant scale, like the Columbia River and Bonneville Dam, or it can be small micro hydros. So we'll look at both a little bit. Here's an idea of the flow that we have in a daily average output. Actually, this is the flow. So here's the Columbia River stream flow. You can see it's highest in May and June when we get those April showers, right? They release a lot of water and we can generate a lot of electricity during that time. We have a hard time storing it still, but we can generate a lot. And that's just going to correlate to the kind of output that we can see through like a Bonneville locks, right? The output's going to be largest when the stream flows are the highest. So for a micro hydro system, we do it a little differently. We divert water from a stream, not necessarily dam that stream up. So it can be a little more friendly depending on how much water you're diverting. But it doesn't, fish can still go up the stream and the critters aren't disturbed as much. Now, if you start taking a lot of water, then that's a bigger problem. But you have some kind of intake, and then there's going to be some kind of required head. That's what creates the energy and creates the potential energy. And then it's going to exit down at a turbine and then re-enter the stream at some point. So it's a pretty simple system. It's used in a lot of developing countries where they need and don't have power grids, but they need these micro hydro systems to provide electricities to small villages, and small communities. So it works really well. Here's a kind of a side view of it and how you could actually calculate the potential energy. And this is one of the calculations you'll do on your project. You do have to have some information, like you got to measure it if you don't have it. So we need to know the vertical head. So it's called head because head pressure is what is created on this tube. So all of this tube down here, if we shut this valve off down here, all of that weight is the weight of the water within the tube, or the vertical head. So we've got to know that, and that's usually in feet. So once we have that, we have to be able to at least understand or calculate the gallons per minute, or the flow. So flow is a volume per unit time. So gallons per minute is a flow. So in this example, it says to estimate the site's potential, power potential, simply multiply the head by the flow, and we need the units correct. So you have to have feet and gallons per minute, and divide that number by 10 or 12. And that's based on, the 10 and 12 is just based on like number of turns in the penstock or the supply tube. How, if it goes up and down at all those kind of things. It works well for larger flow rates, like 30 gallons per minute, which is not huge, but it can be pretty big. And, heads larger than 50 feet. So if you have that, this can give you an idea of what kind of energy you could possibly get out of this system. So let's talk through the system. We have to have some kind of reservoir. So we can make this on the edge of a stream. It'll collect the water, and then it's going to go into a caisson or some kind of intake structure. And that's going to keep rocks and fish and everything else out of there and allow the water into the penstock. So once it comes in, it obviously comes down. You need to shut off at the bottom because you may need to work on the turbine or the generator or, parts of the system that hold that together. We could even have to work on the structural, structural casing that holds the turbine or the generator. So, and then depending on the size or diameter of the tube, and your flow rate, we usually want to neck that down to some kind of nozzle and then target that nozzle directly on the turbine wheel. So Pelton turbines are probably the most common. And I think I have a little video to show you on this. So I'll see if I can get that going. It's a small system, but it's an amazing amount of power that can be generated. So let me see if I can find that. Not to jump ahead here. Yeah, turbo turbine. Let's see what this one is. Oh, student micro highway. I think it's this one. So let's just see what we got here. I don't see any other ones. Yeah. Okay. Let's try it. I think I'll have to put you into slideshow and then click on the turbine itself, and we'll see if we can open that. And then I might.
So let's say you had to read an incredibly long email from your boss that you have to finish before the big meetings.
Yeah, this is the one I want. So I'm not sure you can see it. So I'm going to do a new share to make sure you can see it. All right. Hopefully you can see that. So that's the Pelton wheel. You can see the concrete casement, pretty big and substantial because it can hold back a lot of weight. There you can see the nozzle, so it's coming from a larger diameter down to that nozzle, and it's going to direct it directly on that Pelton wheel. So a whole bunch of pressure can get generated here. I'm starting to turn it on. This is the generator that will create the electricity. Once the system is set up, it literally can run 24/7. So large advantage over solar and large advantage over wind. It's just as long as the water supply is there, it is going to go. So it's a fantastic system, given that you have the opportunity, you know, to use water like that and create that kind of energy. So there's a typical intake, you know, just a homemade small intake. And this is where the penstock would hook up to it. So, all right, so let's just look at it again in general. Kind of the off-grid system. We can go through these starting with, you know, your reservoir somewhere, and then you're going to supply water to a turbine here at number 3, right? And then that energy would head into a battery monitor or a charge controller. Very common because we don't want to, you know, overload batteries. And then once the batteries are full, we have to have somewhere to put the energy. So that's called a dump load. That can be a number of different things. It can be light bulbs. It can be just a dead short works also, but sometimes you heat water or something like that with it. Okay. Then if the batteries are needing charge, it's going to come in here to the battery bank. And then that's going to head to a DC disconnect and a battery monitor to take care of that. So when the battery is full, we send it to the dump load. When the battery needs charged, it gets charged. And then when there's a DC load, it draws from the battery, right? If we want to run 120 volt, then it would go through an inverter and into your household panel. So fairly simple system, very similar to solar. Just, you know, take the turbine away and put a solar panel here and you have the same system. So, all right. I'm going to let you look at this one. This is a fun kind of student micro hydro made out of a garden hose and charges up a battery, which then charges a laptop. So super fun. One more way to calculate power output from hydro. This one is in kilowatt hours calculated by this formula, Q, V, H, and C. So Q being the weight of the water, and it's needs to be in volume per second capacity. So that's a little different than gallons per minute, right? Then there's the velocity of the stream. So they want that in meters per second. And then there is the head, and they probably want that in meters. So again, you can add in an efficiency constant, usually around 50% efficient with some kind of big paddle wheel in a river. So just another way to estimate possible energy production from a small hydro power plant. All right, that should be enough to get you started on your lab that I'm going to create. That lab probably won't come available until Friday or Monday. So this week is all about just trying to understand hydro and finishing up your solar project. So, all right. Take care, and we will talk to you soon.